last week, we will switch the topic to NLP domain, and I am very happy to have one of our colleagues here as the speaker, Jindřich Libovický. And as you see from the slides, the title of the talk is Neural Architectures for Character Level Natural Language Processing. So please, the floor is yours.
Thanks for the introduction. Hi, everyone. You probably know me. I'm Jindřich Libovický. I'm going to talk about neural architectures for character level NLP, which is a topic I worked on during my postdoc at LMU in Munich. And yeah, I'm gonna explain why I think doing character level NLP is interesting, and then I'm gonna introduce our novel approach for neural string edit distance. And the second half, I'm gonna talk about character level neural machine translation. So why doing characters? This is an example how the BPE by segmentation looks like. These BPEs were fitted on the WMT14 English-German data, and when we look at how the text gets segmented, it hardly makes any sense. Like it's a very useful statistical heuristics. It works very well, but if we look at the actual segments, it barely makes sense to split cats into C, that is the beginning of a token, and AT. But it works incredibly well, and probably the reason is that it just makes the input tokens distributed in such a way that the embeddings that get updated reasonably frequently, which is a good property, but anyway, it's still pretty ugly. And when someone sees like that, you must have an impression that we can do better segmentation than that. Also, the success of deep learning in natural language processing is often narrated like as a story of getting rid of any assumptions about the data and letting the data speak for themselves, which is quite disputable on many levels. For instance, if you look at the transformer architecture, it pretty much resembles doing some dependency structures. Anyway, the assumption that really remains is that the input is segmented into words or word-like units or subwords. So if the story of getting rid of assumptions is true, we should be able to get rid of the segmentation as well and only work with characters. And also there are some practical aspects that we would like to get from the subwords. They are like simple processing pipelines without tokenization, learn better and more meaningful segmentation, getting a robustness towards noise, and generalize better for morphology and for some domain-specific vocabularies. However, when we try to do character level NLP, we face some computational problems because the character sequences are much longer than the word sequences, and for instance, with the transformer architectures that compare each token with each token, this makes it computationally really expensive. It works well for word level tasks that do not require some more complicated sentence context like transliteration, generating morphological inflection, cognate detection, which I will show. But for like semantically heavy tasks such as machine translation, it still performs much worse than subwords, despite what many papers on character level machine translation claim. And also, I will show that most of the assumed advantages especially domain and domain robustness and better morphological performance are not true when we do the experiments properly. So this was the introduction why I do care about character level processing methods. And now I'm going to introduce a generalization of edit distance, of Levenshtein distance with neural networks. It is based on a preprint that we made available almost a year ago, and it's a paper that got rejected from 5 conferences. But I still think it's a cool idea, and it's worth presenting in here. So it's a novel model, and the main idea is not to use the traditional models that are used in NLP for the character level task, because usually for the character level task like morphological reinflection, we use the same architectures that we use for the large tasks like machine translation, and these architectures are hardly interpretable. They are sort of heavy-weighted and in general like overkill for tasks which are relatively simple. On the other hand, the Levenshtein distance, it's very transparent, it's interpretable, it puts the toString in explicit relations via the edit operations. Weak and not flexible enough for tasks. Something we would like to fix by this architecture. Just a reminder how the it's done using a dynamic programming algorithm. So for string s and strings s and t, so for the 2 strings s and t of length n and m, we compute the Levenshtein distance by gradually filling a table of dimension m times n. We start by saying that deleting stuff in the string s costs one letter is of cost 1, and then we gradually fill in the table and taking the minimum of the cost of deleting a character, inserting a character, or doing a substitution. It can be better shown on an example. So let's say we want to transcribe a word kitten to a word sitting, and during the computation we fill a table like this. We can see that transcribing the empty string to empty string, it always costs 0. The first column actually shows the cost of transcribing an empty string to sitting. We always insert 1 character, and the cost increases by 1. And this is cost of deleting the word kitten. So 1 letter each costs 1, and in the end we end up with an empty string. These are the simple cases, and now the interesting part. Let's say we want to transcribe the substring kit to substring sitten. We already know the previous costs. So one option is that we already get rid of ki and already written city. So in that case, we would substitute t for n, which would be a cost 4 plus 1, which would be 5. Or we already have sitten, and we just want to get rid of the t, so we would delete it and here replace the cost at the cost 1 to 5, and then we would get 6. And the best option here is that we already got rid of kit. We already have written city, and we just insert n, which would give us the cost 4 that we have here. And this is the algorithm that I use all the time through the rest of the talk. And such a simple approach to add a distance is also very rigid. It for instance, assume that we have the same alphabet for both the source and target string. But if we want to, for instance, transliterate with Praha to Cyrillics, such an algorithm would fail because these are different UTF characters. So we would need to change the algorithm in such a way that it would assign a 0 or almost 0 cost to the operations which are the substitutions that correspond to the same characters. And well, for transcribing Czech into Cyrillics, we can probably do it by hand and handcraft the rules. But in different tasks, it may be more complicated. So there are ways how we can learn these weights. And one of the ways how to learn these ways is a so-called Learnable at a distance from 1998. And this reformulates the added distance as a probability function. So there is a probability one multinomial distribution over all possible operations. They have some probabilities. And every time we do an edit operation, we sample from this multinomial distribution, which means that the transcription of one string to another string is a product of probabilities of the individual edit operations. So instead of having the cost that we sum, we have the probabilities that we multiply. And in practice, it's actually the same because we don't multiply probabilities, but we sum logarithms of the probabilities. And using the same algorithm, we can actually get a best derivation, a best sequence of operations that can transcribe one string into another by just replacing maximum, the minimum with maximum, because we are no longer interested in the minimum cost, but at a maximum probability, and summing the probabilities. Summing the log probabilities. And we can also get a sum of all derivations, of probabilities of all derivations by just replacing the maximum with a summation. And this is important for the actual learning. And the learning is done using an expectation maximization algorithm in a very similar way that all of us have learned in the introductory course to statistical NLP with hidden Markov models. This is basically the same. We iterate over the training data and do the inference with the current model. So given the existing multinomial distribution over the probabilities, we do the inference and find out what is the most probable sequence of operations that transcribes one word into another word. So the data probability increases because it's a better, these are better derivation than we had before. And from this iteration, we can get expected counts of the operations using basically the same forward-backward algorithm as is used for the hidden Markov models. And in the maximization step, we can normalize the expected counts and get a new probability estimate of what operations are probable and which are improbable. This is more flexible. We will learn the weights for the particle operations. The weights are estimated from the data, but the costs are still rigid because the cost only depends on the two characters that we are substituting with each other, or or just the character we are inserting or deleting. And this is also something we wanted to get rid of. So instead, we change the model in such a way that we can backpropagate the error into a contextual neural representation of the characters. So when we have the two strings, in this case, it's English word equal that we want to transcribe to phonemes. So actually, we have the sequences, and now we are interested in how probable is the sequence equal the phoneme sequence given the string. We start by getting contextual neural representations of the symbols. It can be either we can either directly take the embeddings, which is not really contextualized. We can do a convolutional network. We can use a bidirectional RNN, which is suggested in this paper, or we can even do transformers. So we have one contextual vector for each input symbol, and then we use them to get a representation for each symbol pair by concatenating these vectors and doing a nonlinear projection. So in the stage for each symbol pair and the source and the target string, we have a vector representation. And we do basically the same that I showed with the table with what's kitten and setting. We compute the probability that EQ is derived into EQ by just taking the previous the previously computed. Now these are probabilities. These are not the costs. And we multiply it by the individual operation probabilities instead of summing the individual costs. And this is basically how the model works at inference time. But the problem we need to solve is that the original expectation maximization algorithm relied on the discrete table of operations. The trick that actually allowed the algorithm to work was that only some operations are plausible given the two strings. So it means that during training we just never see some symbol pairs. This is trickier with a continuous representation. So we do a different trick. We compute the expected distribution with the forward-backward algorithm the same way as we did before. But instead of normalizing the count, because we no longer have the discrete table, we compute the KL divergence between the predicted the distribution of operations and the expected distribution computed by the forward and backward algorithm. And well, this is the trick how we redo the expectation maximization, and also we directly optimize task specific loss. You will see later what the tasks are. But if it is a string pair classification, we jointly optimize this expectation maximization and the classification likelihood. And if we use the model for string transduction, we also keep optimizing this expectation maximization, and we also optimize the negative log likelihood of these symbols that we want to output. The first task we tested the new string at a distance on is cognate detection. By that we mean for a pair of strings in International Phonetic Alphabet, we want to decide if the two strings have the same diachronic origin. We use databases for Indo-European and Austro-Asiatic languages for that. We sample the positive and negative pairs for training and measure how well the model works using the F1 score. This is a visualization what a trained model can give us. This is again the same table as you saw with the example with the algorithm, but instead of the costs, here we have visualized the probabilities. We can see that for a cognate pair, there are high values for the matching symbols, and we use this very last state as a probability of the two strings being a cognate pair. For a non-cognate pair, we can see that the only thing that is probable is transcribing the empty string to an empty string, and something like fur might be similar to this p, but as it goes on, it actually ends up with almost zero probability. And this terrible table that I didn't have time to visualize better shows how our model works compared to other models. This is the original statistical learnable at a distance, which works surprisingly poorly. This is what we can get using the standard transformer, which is hardly interpretable. And this method we are comparing with is a state-of-the-art interpretable string pair classification method that, similar to our method, can get also an explicit alignment between the source and target string. They use some synchron distance approach to get the alignment, and we get our best results with contextualizing the representation using recurrence networks. Surprisingly, the transformers are worse, but I think this is mostly due to some training instability that the gradients that we get from the expectation maximization algorithm are quite unstable, and the transformers are sometimes also numerically unstable, so it makes it hard to optimize with transformers. And unlike the next task that I'm going to show here, the model would work actually almost the same, even if we didn't do this complicated expectation maximization and only optimized for the last state to have the correct probability. So this was cognate detection. The other task was string transduction. We tested it on Arabic to English transliteration with 13K training examples and grapheme to phoneme conversion on an old and standard CMU dict data set, which is approximately 10 times larger than the Arabic to English transliteration. And the evaluation here was a little bit tricky because there are multiple possible phoneme sequences for the strings. So the standard evaluation is that you do the transcription, then you find out which one of the possible translation is the closest, and you compare with the closest one. And the evaluation metrics that are used for that are word error rate and character error rate. To do the string transduction, we had to do some minor modifications of the models as well. So instead of using the bidirectional representation on the target side, we need to contextualize the model only in a single direction, which means in case of RNN, we use just a single directional RNN. With transformers, we need to do the causal masking. And also the deletion probability must not depend on the last target character. So we don't consider the deletion probability when emitting the next symbol, and only compute the probability post hoc. And there is another dirty trick to make it work, that we add attention from the target to the source representation in computing the contextual pairs, or the string or the symbol pair representations. This is again an ugly table that shows how the models worked for transliteration. And we can see that we were almost able to match the performance of the sequence-to-sequence models. Also, due to the expectation maximization algorithm that requires drawing this quadratic large table again and again, it's much slower than doing the standard sequence-to-sequence learning here. And the results for the grapheme to phoneme conversion are pretty much similar. Again, this is roughly 2 times slower than the sequence-to-sequence models, and the performance is not that good as the sequence-to-sequence models. But here we can also measure how well the phonemes and graphemes are aligned. So given a statistical alignment of the graphemes to the phonemes, the neuro-added string models can much better recover this alignment compared to the sequence-to-sequence models. If we look on how the alignment looks like, it can be like this with an RNN-based model. So what the model learns is that it is good in matching the vowels to get the consonants together, and the vowels are pretty much randomly inserted and deleted. And this is also a short ablation study which shows that in this case, the expectation maximization loss, or this type of optimization, is really crucial for the model to work well. So this was neuro-added string distance. Probably it's a good time if you have some questions about this part to answer them now before. But it's already fixed, isn't it? Okay. All right. So let's talk about machine translation now. The stuff I'm going to talk about is based on 2 papers. One is about training character level models by starting it with subword models. It was a short paper presented at NLP 2020. And other insights are from a very recent paper that is sort of a meta survey of what people did and when, and an evaluation of how the state of the art really is. And it's a paper that just got accepted to findings of ACL 2022. This is a timeline that shows research papers and WMT submissions that discuss character level methods. The most influential neuromachine translation papers are from the late 2015, and we can see that already in 2016 there were several papers discussing character level methods. in WMT 2017, there were quite some papers using character level methods. Then there was some research activity. Again, this is an important milestone because the transformer architecture was introduced. Here, the BERT model was introduced. And it took some time before researchers started to be interested in using character level models with transformers. And very recently, there are also some work trying to do something like BERT, a pre-trained representation model with characters. But after 2017, there are basically no WMT submissions that would use character level methods. And the research paper often report parity or outperforming the subwords model, but it's only true for the data set that are used in the research papers, which are usually smaller than those used for WMT. And also there are other reasons why the character level models are not used at WMT, which is that not only the worst quality, but also they are 5 to 6 times slower from our measurements, which would mean that the participating teams would be able to do less iterations of back translation or less iterations of knowledge distillations, which is probably more valuable that what they could get from using the characters. And this shows how often different segmentation was used at WMT in different years in all the translation tasks. So the subword models clearly dominate. Every year there are some approaches that try to use more morphological segmentation. Typically these are used for Finnish. And word-based and character-based models are very rarely used. This is just a fun fact, nothing very relevant, but the average vocabulary size of the systems at WMT slowly decreases, but no way to the number of characters because still the median vocabulary size is 32,000 items, and the reason for the decrease is probably that there are more and more low resource languages in WMT, and small vocabularies work better for low resource languages. Now I will pause with the criticism of other papers for a moment, and we'll talk about the curriculum learning that we did for character level machine translation, which later motivated further experiments. But the main idea of this approach is to train a subword model first. So the model knows what the words are. And in the second stage, fine-tune the model to only use characters. The motivation for that was that we experimented with using different vocabulary sizes, and noticed that there is once we drop the subwords completely, there is a large drop in performance. We did our experiments with English to German translation on the WMT 14 data, English to Czech translation with the Czech 1.7 corpus, and English to Turkish with a pretty small corpus of 207,000 sentences. And we hope that we will see something interesting because Turkish is an agglutinative language, and the assumption that the character level models could be better for morphology might be important here. But this is the reason. This is the result I already talked about. That as we decrease the vocabulary size that we see here, the translation quality slightly drops. And once we go from 500 BPE units to the character level, there is a huge quality drop. And if we instead gradually fine-tune the subword models and slowly reduce the vocabulary, we end up to a much better model, which is still worse than the subword models. The trend is similar if we do the translation in the reverse direction. It's also the same for English to Czech translation. With the English to Turkish translation, it was not so clear because the character models themselves did not work that bad. So we sort of hoped that this is because of Turkish being the Turkic language, but later last year when we did experiments for the WMT low resource task, we replicated the experiments with Russian and Chuvash, and the results with Russian and Chuvash were basically the same as with Czech or the other languages. So this result is probably an artifact of the Turkish data set. And the only positive property of the character models that we observed was that it's much less sensitive to source side noise. So if we sample synthetic noise to the source sentences and measure how the translation quality drops, the character level models are not that affected as the subword models. So this sort of preliminary experiments made us think that semantically rich units are crucial during training, even though they can be sort of unlearned eventually. So if we want to avoid using subwords for the models, we should get similar units as the subword units from the characters themselves. So we need to modify the architecture in such a way that the input of the transformer would be something like subword embeddings without actually having the subwords. And this led us to the experiments with different character level architectures. The one we started with is a pretty old architecture from 2017, which is one of the first experiments done with character level machine translation. And it uses convolutions of different kernel size, then something that's called highway layers, which is then followed by max pooling. So this part of the architecture gives us one vector per character in context of some character span. And this downsampling max pooling part, it just takes the window of 5 vectors, the 5 characters, and that's the maximum over time. So we end up with a sequence which is 5 times shorter than the input sequence, which should emulate the subwords. Mám to strčit do mezi ty dva profíky. No, jo, no to víš. Ještě víš. No, to bylo by dobrý. No. Oho. Slyší to. Jo, odpadl mi poslech, tak to nic. Pokračuj, prosím. All right. So we end up with a sequence which is 5 times shorter than the original character sequence, and the vectors that we get are supposed to emulate the words or the word-like units, subword units, whatever. And it was successfully used with RNNs. It matched the performance of that day's BPE-based model, and this is also the architecture that was used in the 2017 share tasks. Oh, what did I do? I clicked the link. The other architectures that we use, one is called CANINE. I forgot what the acronym was, but yeah, it's an architectural design for pre-training an encoder-only model, something like BERT, and it was published in a preprint from Google, which was not accepted yet anywhere. And the model that they get from this architecture shows really strong multilingual performance. So they use it for multilingual representation model, and it uses quite similar building blocks as the previous architecture, except that they are like more recent or more modern or whatever. They start with character embeddings, which they get from some hashing. Then they have something that they call a local transformer. So the usual transformer like compares all the input states with each other, which means that there is a quadratic number of operations. But here it's done on the local list. So for a window of characters, they do this comparison, and it is downsampled, not using max pooling as in the previous case, but using a convolution with what's quite a large kernel size, but with small stride. So in this way, they also get a shorter sequence of vectors. And the third architecture we experiment with is called Char-former. It's also from Google. It will appear at this year's iClear. They also use it for training model, which is supposed to be like BERT, and it's very parameter efficient. There is one convolution at the beginning, and then the only operations that they do is averaging the embeddings. So they group the inputs into so-called blocks, and here the embedding of the block of size 2 is the average of these 2 embeddings. And they do blocks of size 3, which means they take three neighboring embeddings and average them. And once they have these average blocks, they take those averages and average them like in the orthogonal axis, and this is how they arrive with the sort of contextualized or locally contextualized character embeddings, and then they do max pooling to get shorter sequence again. So these were architecture innovations that we took from the works of others, but they only work on the encoder side, all of them. And we wanted to have a similar architecture also on the decoder side, because the character level decoding is terribly slow compared to some words. So we came up with an architecture which works like this. The decoder takes the characters, it processes it with a character processing layer, which produces the shorter sequence, and then this shorter sequence is processed with a transformer decoder, which again which produces some latent states, and these latent states are then processed to a very lightweight LSTM decoder that actually generates the characters. So here the downsampling factor is 3. So we process 3 characters, get 1 decoder state, and this small LSTM generates 3 characters, which are then put in the input of the large decoder, shrinked into 1 state, put to the decoder, and again we generate 3 characters with the LSTM before we put them to the input of the decoder. We experimented with the architecture with a small data. We used IWSLT14 data for translation between English and Arabic, French, and German. And by small data, I mean 200,000 sentences for training. And we implemented everything ourselves in PyTorch. These are the results that we get in terms of BLEU, but they are the same in other metrics as well. We managed to have the 2-step architecture, the 2-step decoder, as fast as the BPE, which is a good news. But on the other hand, it was much worse in terms of the translation quality. And if we compare the character processing architecture, it appears that that the oldest one, the one from 2017, is actually still the best one. If we compare the different languages, the only language where the character level models were better than subwords was Arabic, and in all the other languages, the subwords are always slightly better than characters, and the best character level architecture uses the old shrinking method in the encoder and directly characters in the decoder. So the conclusions from the experiments with the architectures is that the least style encoder works the best, and the 2-step decoding matches the speed, but the quality is much worse. So we took our best architectures from these experiments and used them in a large-scale experiments with WMT data. As I said at the very beginning, the previous work typically makes optimistic conclusions about the character level models based on small data. So we wanted to evaluate it properly on the data sets that are actually used in the WMT competition. So we took, for English Czech, we took the Cheng 2.0 corpus with 61 million authentic parallel sentences and 50 million back translated sentences. We didn't use the forwards translated. For English to German, we used the data mix from Edinburgh that they used for the WMT 21 submission that actually Indra gave to me. 66 million authentic parallel sentences and 52 million back translated sentences. Just a reminder, the previous experiments were done only on 200,000 sentences, and these are tens of millions. So this is almost what's used in the WMT submissions. We did text back translation. We used the transformer big architecture and used FAIR-seq for the experiments. Most of the papers on character level machine translation motivate their experiments with morphological generalization and noise robustness, but almost none of the papers actually does any measurements that would confirm that. They just say it's our motivation, and they never measure that. We wanted to measure everything carefully, so we measure the translation quality using several metrics in several domains. We also evaluated on a gender data set, which consists of sentences with coreference. in some stereotypical cases, we used Morphoval to have a look at specific morphological phenomena. We measured recall of novel forms and lemmas, by which I mean forms and lemmas which did not appear in the training data, and the translation quality under noise that was sampled on the source side. And these are the results for the English-Czech translation. And we can see that the BPE-based model is still the best, and not only for the news translation, but in all the 3 domains that we tested, it also better captures the gender in coreference. There is basically no difference in the Morphoval benchmark, and basically no difference in the recall of novel forms and lemmas. From the character level methods, we still can confirm that the least style encoding is the best method we can do, including the noise robustness. The results in German are actually similar to what we observed in Czech, but it seems that in German there might be slightly better morphological generalization. The coreference, the gendered coreference is much better here. And if we average over the morphological phenomena in Morphoval, we also get a slightly better number, but there is like no systematic pattern. For instance, I hope that the character level models might be better for German compounds, which was actually not the case. And the recall of novel forms and lemmas is pretty much the same in all of the models, but this is probably not that important in German as it was in Czech. And again, under the noise sampled on the source side, the character level models are much better. So the main takeaway from this experiment is that almost none of the usual motivations for doing character level machine translation, like morphological generalization and domain robustness, is actually true. The only thing why the character level models are better is the noise robustness. And this is basically everything what I wanted to say. So to summarize, we came up with a neurostring at a distance, which might be an interpretable alternative for some character level tasks. Machine translation seems to need some semantically rich units and work on shorter sequences. Modern architecture for character level processing that work well in other tasks, especially in the pre-trained representations, does not work that well in machine translation. The best character level architecture for machine translation is the good old least style encoding. Many research papers about character level MT tend to overclaim, and the only clear advantage of character level models is noise robustness. So that's it.